Okay, so the final part of this week's topic is to discuss the method of variation of parameters to solve for the non-homogeneous second order linear ODE, where we cannot use the method of undetermined coefficients. Okay, so method of undetermined coefficient is only applicable to limited type of functions. So if we have more complicated function on the right hand side of the ODE, then we need to select another method, which is the method of variation of parameters. So some example of the more complicated functions include tangent functions. So previously in the method of undetermined coefficient, you only deal with sine or cosine, and the mixture of polynomial and exponential previously by multiplication, addition or subtraction. But if there's a mixture of polynomial and exponential function by division, or it involves some logarithmic function on the right hand side, so you cannot use the method of undetermined coefficients. We need to try this method of variation of parameters. So what is the method of variation of parameters? So this is the procedure. Right, so first, if you're given this ODE, so a as a function of x times the second derivative of y with respect to x, plus b as a function of x times the first derivative of y with respect to x, plus c as a function of x times the y function, equal to a more complicated function of rx at the right hand side of the equation. So these are the steps. So first of all, you need to write the given ODE in a standard form. This is the standard form on the right hand side here. So notice that the coefficient for the d2y dx squared is 1. So you shouldn't have anything in front of the second derivative. After that, you compute the complementary solution, i.e. you solve the homogeneous part first by letting right hand side equals to 0. So you get this yc like what you normally did in the the previous section of this video. So you get y1 and y2. And this step is where it is the method, the methodology of the method. So you need to compute the particular solution. So in this case, yp equals to u1 y1 plus u2 y2. So u1 y1 u2 y2 are all functions of x. So what is u1? So u1 as a function of x is this. So basically in this method of variation of parameters, you just follow the recipe as it is. It's like, okay, first of all, do this. Second, find this. And then third, follow. Okay, you need to find u1. So what is u1? Is the integral of rx. What is rx? It's just simply the right-hand side function of your ODE. And then what is y2 is what you already got in the second step. It's now divided by the Wronskian. So this is not the first time you will see a Wronskian determinant. So yeah, this is the definition of Wronskian determinant. And also U2, Rx, Y1 and W. So here there's a negative sign for U1 and Y2, whereas for U2 there's no negative sign and it's Y1. So but however, it is time consuming and there is no guarantee that you can solve the integration analytically. Okay, there's no guarantee, but this is our next best shot instead of just doing other method like numerical method or graphical method, iteration and stuff. So we try this one first if we can solve the ODE analytically. So let's do an example straight away. So in example 6 here, we have 2 questions. So let's do the first question. Okay, so first of all, as usual, we do the homogeneous part first. So m squared plus 2m plus 1 equals to 0. Check the b squared minus 4ac is 2 squared minus 4 times 1 times 1. 4 minus 4 equals to 0. So you have 2 repeated real roots, it seems. Okay, so it's m plus 1 times m plus 1 equals to 0. So m1 equals to m2 equals to negative 1. So whenever you have this, your yc is then c1 ex plus c2 x e x, or negative x, sorry. Okay, so now from this yc, your y1 is e negative x, and your y2 is x e negative x. So we don't take the coefficients C1 and C2 when we want to define the y1 and y2 to compute the Wronskian determinant. So from y1, you can find out what is dy dx minus e minus x, and dy2 dx is, this one you need to use the product rule, negative x e negative x plus e negative x. So then you compute the Wronskian determinant, which is y1 dy1 dx, y2, y2 dy2 dx. So you put in the expression. So y1 is e negative x, dy1 dx is negative e negative x, y2 is x e negative x, dy2 dx is negative x e negative x plus e negative x. Is it? Yeah, okay. So the determinant is this times this minus this times this. So yeah, do it. E negative x times minus x e negative x plus e negative x minus okay, and you get so end up with just e negative 2x. This is your w. Then so your and we need to do the u1 and u2. You see, just follow this methodology here. Okay, so let's find u1. So u1 is this. So u1 is the integral of r of x times y2 over w with respect to x. So your rx is just the function given to you in the problem. Okay, and your y2 is x e negative x, and then your Wronskian determinant is e negative 2x, integrate with respect to x. So luckily you can eliminate these terms. So you integrate x ln x dx. Okay, so you need this one, you need to use the integration by parts. So you define u equals to ln x, so du is 1 over x dx, and dv equals to apa? X dx, just v is x squared over 2. So u1 is negative integration of x ln x dx equals to negative the integral of u dv equals to negative uv minus integral of v du, negative. So u is ln x, v is x squared over 2 minus the integral of v x squared over 2 du is 1 over x dx. So this one you can eliminate, and then you end up with ln x times x squared over 2. So you integrate x over 2, x squared over 4. Yeah, that's it. So it's negative x squared over 2 ln x plus x squared over 4. So this is your u1. Next, you compute u2. So u2 is integral of r of x times y1 over the Wronskian determinant and with respect to x. So integrate the e negative x ln x, y1 is e negative x, and your w is e negative 2x dx. You can delete this. So you integrate the ln x dx, so you need to use the u substitution as well. So u equal to ln x, I mean not u substitution per se, but integration by part, I mean. Okay, so dv is just dx, so v is x. So then the integral of ln(x) is integral u dv equal to uv minus integral of v du. So your u is ln(x), v is x, so I'm going to put it in front, minus integral of v is just x, du is 1 over x dx. Yeah, so x ln(x) minus integral of 1 is just x. So this is your u2. So you got u1 and you got u2. Go back to the methodology. What do you have? So your yp. So yp is u1 y1 plus u2 y2. Okay. So your yp is u1 y1 plus u2 y2. So your u1 was this. Okay. So your u1 is negative x squared over 2 times ln(x) minus plus x squared over 4, and your y1 is e to the minus x, plus your u2 is x ln(x) minus x times your y2 is x e negative x. Betul ke? Yeah. Okay. So then you simplify and collect all the terms together. And just try to simplify stuff, so you get and then you put this x inside, so that you will just have the e to the minus x outside. So you have inside is x squared ln(x) minus x squared. So then you can simplify further. So here ln(x) and this one so x squared minus x squared over 2, you get x squared over 2 ln(x), and this term with this term, then 1 over 4 minus 1 is minus 3 over 4. X squared. So this is your yp. Then your y total is yc plus yp. So your yc is c1 e to the minus x plus c2 x e minus x plus e to the minus x times everything here. Okay, so this is your y total. Okay. So this is for example 6, number 1. So for example 6, number 2, you can refer to the notes here for method of variation of parameters. Okay. So basically, because it's so methodological, I mean, all you do is to follow the method, the steps. So try to follow the method. You do the homogeneous part first, and then you do the non-homogeneous part. You identify what is your R, and then you find out the Wronskian, you find the U1, you find the U2, and then finally your YP is U1 Y1 plus U2 Y2, and that will give you the YP. And finally, when you answer, the total solution is YC plus YP, then you combine this is your YC, and then this is your YP from the method of variation of parameters. Okay, so but as an engineer, of course, you can use computer programs to do all the hard part of the calculations, but then you need to know how to select which model, which method, how to model the physical system, and how to interpret the data. So for that purpose, you can read on in this example. Okay, so it says here, in engineering application, learning mathematics tool is just a strategy, and it's not the main focus. because it can be done by the mathematician, by the computer scientist, whenever you have an algorithm, because everything is AI now, right? But it's important for you to evaluate and justify the appropriateness of the selected tool, and also to interpret the result and data analysis. So you can read the examples to help you to interpret the data. Okay, so here you can see that it is transient until it reaches steady state because it doesn't change with time. So this is, yeah, you just need to read, because otherwise I'm going to just read the whole thing here, which is, well, it's just not useful lah. And you can read further in these appendices. For chemical engineering student, you may be more interested in example 1 and 2, liquid system and a mixture problem. However, the ones that you also can relate better is the vibrating spring with and without damping, and whenever there's a forced vibration. So you can relate what kind of system can be represented using first order or second order ODE. Okay, because in the exam, you're not going to just be given the equation for you to solve, but you will be given a problem for you to model the solution using ODE. So an example that I can share here is for this example. So you can read this example, you can try. So in this case, you are given the ODE. So this is non-homogeneous. So you are given all the coefficients. You just need to put it in terms of dx dt and dx squared dt squared, and find the complementary and particular functions solutions. So we will discuss this example in a separate video, but you can try to do this first on your own, because you have all the basics covered. You know already how to apply the methods. So hopefully you can take some initiative to apply it into some engineering situations. Okay. So some reflection after we have finished the whole topic on solving ODE, second order, homogeneous and non-homogeneous. So you need to know the vocabularies, and you need to recap the strategies to solve first order linear ODE, which is in our previous week's lecture. And in this lecture is to solve second order ODE, homogeneous and non-homogeneous. So what are the strategies and why do we need to learn the strategies here? So just do your own reflection on what is the importance of learning all of this. Okay, it's not just for fun, although it's quite fun and oddly satisfying to be able to solve a hard problem, but that's just not it. You're going to have to apply it in later years in your course. Okay, right, so thank you for listening. So this is the final part of the video, so hopefully it's useful to you, and all right, bye bye.